the Lewis structure is a representation of the total valence electrons obtained by counting the valence electrons of all atoms involved. The Lewis structure is responsible, the Lewis theory is responsible only for the distribution of the total valence electrons and not on the position of these valence electrons. And we studied for several possible Lewis structures. We have one of the structure which is the best, and this can be found by using by calculating the formal charges of all atoms in the structure. Problems with the Lewis structure is to say that Lewis structure has inconvenience. For this reason, we have to pass to another theory, which is the VBT, the valence bond theory. Lewis theory draws only the distribution of the total valence electrons in a molecule. It's not responsible for the distribution of this valence, so it's not responsible for the type of these bonds. And if we don't know the type, or we are not interested in the type of bonds, so LT, the Lewis theory, does not give good predictions in the bond strengths and bond lengths. The bond strengths is the energy needed to break this bond, and the bond length is the bond distance. Lewis gives good approximations of the bond angles. We can have approximations, values, but usually cannot be used to get the real angle. It cannot write one correct structure for many molecules in which the resonance is important. The resonance structures are structures of the same molecule that differ in the placement of the valence electrons. So Lewis could not explain which of these resonance structures is the best. We use the formal charge in order to know. So this is inconvenience. It does not predict the magnetic behavior of the molecule. For example, according to Lewis, oxygen, Lewis structure predicts that we don't have single electrons. So O2, according to Lewis, is diamagnetic, but the experiment proved that oxygen is paramagnetic. So this is the inconvenience of Lewis theory. For this reason, we will pass in the next chapter from the LT, the Lewis theory, to the VBT, the valence bond theory. Why? In order to give answers to these inconveniences. Structure determines the property. The aim of this part is to know the geometry of a molecule. When we draw, for example, CO2, according to Lewis theory, we use the plane XY, so this is two-dimensional plane, and we can write the bond in a way. We are not interested in the bond angle. We are not interested in the geometry. We are only interested in the distribution of the valence electrons. So to know the property of a molecule, we have to know its real structure. We have to know its real geometry. So the question now, what what is the real distribution of the outer atom around the central atom. So what is the real structure of this molecule, or what is the geometry? The structure is important in order to know several properties. For example, the polarity of a bond, or the polarity of a molecule, or its reactivity. Some molecules are very reactive. And sometimes to explain this high reactivity, we study the geometry of this molecule, and from the geometry we can have conclusions. Another property, you consider, for example, ethanol. Ethanol is miscible with water, and oil is not miscible. So to explain the problem of miscibility, we have to explain the polarity of each molecule. And to have the polarity, we have to pass by studying the structure. We pass to very important part, which is the molecular geometry. The property of a compound are very much determined by the size and the shape of this molecule. The molecular geometry can explain the strengths of this bond, so we can know the bond length or the bond distance, and the geometry explain the bond angle between the outer atoms and the central. So we'll focus on the molecular shape, which depends on the bond angles, and as a reference, the geometry of any molecule by convention is represented according to the central atom. Suppose I have 5 students in a classroom. I can ask, what is the shape of this classroom? So I choose the central student, and around the central students, the other students are called the outer students. So the geometry of the classroom will be represented by the geometry or the form obtained of the outer atom according to the central one. We have several representations. Consider, for example, H2O. When we write H2O, this is the chemical formula. When you write Lewis, okay, we have 2 other electrons. We have 2 pairs of electrons around oxygen, which are the non-bonding pairs. So we describe only the bond between HO and OH. We are not interested about the angle. You can write the angle 90, 80, 180, as you wish. So this is the Lewis. And H2HOH is called the structural formula. We have another representation that describes the geometry, which is ball and stick model. So the atoms are like balls. So we write OH, H as balls. And in this case, when we talk about the geometry, we have to determine exactly the angle and look to the difference between the first structure, which is the skeletal formula. We are not interested in the geometry, and the ball and the stick model, we have to determine the angle. We have another representation, which is the space filling model. We write dash between 2 atoms, between oxygen and hydrogen, and this dash is 2 electrons. is the probability of presence of electrons. This is not a dash. The dash is a representation. So between oxygen and hydrogen, we don't have space. We have probability of bonds to find the electron bonding. So we have oxygen that is directly bound to hydrogen and directly bound to the second hydrogen. So this is the space filling. We fill the space between the atoms, and this is the representation. In our study, we will use only the ball and the stick model in order to describe the structure or the geometry. For water, Lewis, ball and stick, space filling. For ammonia, this is Lewis. Yes, of course, you have to complete. If you write Lewis, you have to complete the non-bonding electrons on nitrogen and non-bonding electrons on oxygen. So this is structural formula, ball and stick, space filling. For methane, this is a structural formula, ball and stick, and space filling. So the objective is to find the geometry according to the ball and stick model. And when we ask to find the geometry, you have to write the name of this geometry. For example, linear, trigonal, planar, tetrahedral. So you have to write the name. Second, you have to determine the angle, the bond angle. For example, in case of CH4, the name of the structure is tetrahedral. The bond angle is 109. What is the VSEPR model, or simply the VSEPR model? V means valence, S shell, E electron, P per, R repulsion. The geometry of the molecule is described first by writing Lewis. And when we write Lewis, we are interested only between the valence electrons of the atoms involved. And these electrons are grouped into pairs, non-bonding pair or bonding pair. And this pair, these pairs or these electrons are charged negatively. So we will have repulsion between the valence electrons in a molecule. And this repulsion is minimum. When this repulsion is minimum, so the atoms are well arranged according to the central, and therefore we obtain the geometry. So to find the geometry, we use the VSEPR method, or we use the principle of the repulsion between the pairs of electrons of the valence shell. This is a simple and effective model for predicting the molecular geometry. The first assumption of VSEPR, VSEPR, and this is the abbreviation of the model, but the person who discovered this method is called Gillespie. This is the rule of Gillespie, or the VSEPR model. According to VSEPR, a molecule adopts the geometry where the repulsion between the valence electrons of all atoms involved is minimum. And as I said, we have several types of electron pairs. Consider CH4. we have 2 electrons between C and H, 2 electrons between the single CH, 2 electrons bonding CH, 2 electrons bonding. So 2 dots are called the bonding electrons, and it's 2 electrons bonding form 1 pair bonding. So we have 4 pairs of bonding electrons, or in total we have 8 electron bonding. In case of nitrogen, we have lone pair on the nitrogen, and this lone pair or non-bonding electrons is not involved in the bonding, so it's called non-bonding pair or non-bonding electrons. So around carbon in the first CH4, the number of electron pairs is equal to 4. And in these 4 electron pairs, we have 4 bonding pair and 0 lone pair. We don't have lone pairs. In the second example, what is the electron pairs around nitrogen? The electron pairs is 1, 2, 3, 4. And in these 4 electron pairs, we have 3 pairs bonding and 1 pair non-bonding. Pay attention, we will consider that the 2 electrons bonding between carbon and hydrogen are found in a balloon. This balloon describes the probability of points to find this 2 electron bonding. So the 2 electrons are found in a balloon or in a lobe, and the lobe contains 2 electrons. So what are the types of bonding in the CH4? First of all, you have to calculate EP, the electron pairs. EP equal, in case of carbon, 1, 2, 3, 4. So the carbon has EP equal 4. In case of nitrogen, EP is equal to 4. 1, 2, 3, 4. But pay attention, in this EP equal 4, we have 3 NBP, 3 non-bonding pair, and we have 1 BP, 1 bonding pair. I return to the example. What would happen to these bonding electrons around carbon? These 2 electrons are charged negatively, and the 2 other electrons are charged negatively. We will have repulsion, and repulsion between these 2 electrons and this pair. So we will have repulsion between these pairs. The molecule will vibrate around, the atoms will vibrate, the outer atoms will vibrate around carbon because we have repulsions. When the repulsion is minimum, the figure of the molecule is constant, or the outer atom stop vibration around the center, so the molecule will take a certain known geometry, which is, in this case, tetrahedral. I will pass to the second example. I will have repulsion between the lone pair and these 2 electrons. Lone pair, these 2 electrons. Lone pair, these 2 electrons. Also, we will have repulsion between the bonding electrons. So the hydrogen will vibrate around nitrogen in a way to have a minimum repulsion. When the repulsions are minimum, the geometry is stable, and as you look, the geometry is as a pyramid. So VASPER is based on the study of all types of repulsions in the valence electrons around the central atom, and when these repulsions are minimum, so we obtain what we call the structure of this molecule. We have 5 basic arrangement of electrons around the central atom. We have 5 basic. To remember that 2 electrons between 2 atoms is 1 electron pair, so EP equal 1, and these 2 electrons are drawn in a lobe or a balloon. Based on a maximum of 6 bonding electron groups. In your curriculum, in the first year, you can have a central atom with 2 electron pairs. Or around the central atom, we have 3 electron pairs, so EP equal 3, or EP equal 4, EP equal 5, or EP equal 6. So the maximum electron pairs around the central atom in the curriculum chemistry of the first year is 6. There may be more than 6, but this is not our study. I consider this nitrogen, NH3. I have non-bonding pair, so non-bonding pair equal 1. I have 3 bonding pairs, so BP equal 3. The total EP is the addition of all pairs, so we have EP equal 4 around nitrogen, the non-bonding pair equal 1, and the bonding pair equal 3. This is the first step in finding the geometry, is to know EP around the central, NBP, and the BP. And this can be obtained only if you draw well the Lewis structure of an NH3. So pay attention, Lewis structure is very, very important. Figure of repulsion versus geometry. What is the figure of repulsion? The figure of repulsion is the drawing of all types of electron pairs around the central atom. We draw the non-bonding pair, the NBP, and we draw the bonding pair, the bonding pairs, the BP. When we draw all EPs around the central, this is the figure of repulsion. Why the figure of repulsion? Because this is the repulsion between all types of valence electrons around the central. The geometry is different. The geometry is the drawing only of the bonding pairs. For example, consider this figure. I draw 2 electrons bonding in lobe, 2 electrons in another lobe, 2 electrons in the third, and also I draw the non-bonding electrons in a lobe. So I draw all types of bonding pairs. This is the figure of repulsion of the NH3, and as you see, the figure of repulsion is tetrahedral. If they ask us to find the geometry, I have to erase the bonding, the lobe of the non-bonding, so I obtain this figure. If you look, I draw only the bonding pairs. So in the first, the figure of repulsion of all pairs is tetrahedral, but the geometry is not tetrahedral. The geometry is as a pyramid where the basis is triangle, so the geometry is a trigonal pyramidal. We have difference between the figure of repulsion and the geometry for the same molecule. In one case, we can have figure of repulsion equal geometry if we don't have non-bonding pair in the structure. So the geometry, I noted GE. The figure of repulsion, I noted FR. The geometry or the shape is only the drawing of the bonding pairs around the central atom. When the central atom does not have lone pair, so the number of bonding pair equals 0. In this case, the figure of repulsion is the same as the geometry. I will pass to the 5 possible arrangements. First, linear arrangement. Consider beryllium Cl2. To know the EP of beryllium, we have to write the Lewis structure. Beryllium Cl2 Lewis structure is the following. If we look to the central atom, we are interested only in the central atom, which is the beryllium. What is the EP? How many pairs we have around beryllium? This is one bonding pair and one bonding pair. So EP around beryllium is equal to 2. In the EP, we have 2 types. We have the BP, which is the bonding pair is equal to 2, and the NBP, the non-bonding pairs, which is equal to 0. We don't have non-bonding pairs around beryllium. So in case of beryllium, we have 2 pairs, so we have 4 electrons around. 2 electrons in each side or in each balloon or in each lobe. In your opinion, what is the minimum repulsion between these bonding electrons? If I have 2 electrons around beryllium and 2 electrons from the second side, the minimum repulsion is when beryllium Cl is linear. So they will occupy position opposite each other. So the central atom is at this point. In the first balloon, we have 2 electrons pairs, 2 electrons bonding, and in the second balloon, we have 2 electrons bonding. So the best structure, the minimum repulsion is when these 2 balloons are 180 degrees. So the figure of repulsion in this case is linear. And since we don't have lone pairs around beryllium, so the geometry is the same of the figure of repulsion, and the geometry is also linear. And we have, when we talk about geometry, we have to determine the angle CLBE-CL, or outer central outer atom, is equal to 180 degrees. So this is the linear arrangement. Should we do the same work or the same analysis for any molecule? No. Now we will study a method, a very simple method to find this arrangement. To find the figure of repulsion or the geometry of a molecule, transform the molecular formula to the type AXMEN. What is A? A is the central atom. X is the outer atom. M is the number of outer atoms. E is the non-bonding pair. N is the number of non-bonding pair. So what is the AXMEN for this molecule? A X2 E0. A X2 E0. A is beryllium. X is Cl. How many X do we have? How many Cl? 2. E is the non-bonding pair. Do we have non-bonding pair? No. So E0. The simplest or the simple form of the molecular formula is represented by AX2 X2 E0. What is the meaning or what is the importance of this simple molecular formula? Any molecule in the question that has the simple representation AX2 or AX2E0, that means the figure of repulsion of this molecule is linear. The geometry of this molecule is also linear and the bond angle is 180. Suppose they give us, for example, CO2. Should we do all this analysis? No. For CO2, I can write Lewis. I have C double bond O and C double bond O, and this is described in the previous examples. So what is the simple molecular formula of CO2? It looks as AX2E0. So CO2, the molecular form of CO2 is AX2 or AX2E0. Without doing all this analysis, I can say that for CO2, the molecular the figure of repulsion is linear, the geometry is linear, and the bond angle OCO, outer atom, central atom, outer atom, OCO is equal to 180 degrees.